Correct. So,
colleagues, ladies and gentlemen, a very good morning to all of you. Let me introduce myself. I'm Go Se Song. I'm the chair of the Faculty Teaching Excellence Committee. In case you do not know who I am, I'm the person who sent you the invitation to this teaching workshop. So once again, we are here for our Faculty of Science annual teaching workshop. To borrow a phrase that I learned from my good friend Yap Wong Peng. Yap Wong Peng has been mentioned. He mentioned that this is indeed an eventful week of teaching-related activities in the Faculty of Science. And yesterday, we hosted the OSET Roadshow, which some of you attended. And today, we're going to have a double event which comprises our Faculty of Science annual teaching workshop in the morning, and then the NUS Teaching Academy Roadshow after lunch. So I hope all of you will stay for the NUS Teaching Academy Roadshow as well. Now, welcome to the Faculty of Science annual teaching workshop. This year, the theme of the workshop is on teaching the sciences today. The sciences and science education throughout the world, as well as within NUS, have undergone much development in the past 20 years. There are new areas of interest. There is a stronger emphasis on interdisciplinary approaches and also new pedagogical tools leveraging on technology. At the same time, our students are very different from the students that we had 20 years ago. They are technologically savvy. They use the internet and social media extensively. They have the ability to multitask, but their attention span is also very short. With this overall changing landscape in the sciences, ranging from the disciplines itself, the curriculum developments, technological and pedagogical advancements, and to students' learning habits, the fundamental questions would then be how we can adapt and how we have adapted in our teaching for it to remain as both relevant and effective. In today's workshop, we have speakers and panelists to provide a range of perspectives to these issues. They include Professor Alex Yip from the Department of Biological Sciences, who has more than 35 years of teaching experience in NUS. That's amazing, huh? And Dr. Vic Gopal from the Department of Statistics and Applied Probability, who represents the new generation of our science educators. Professor Chan Lai Hua from the Department of Pharmacy will also share her many years of teaching experience during the panel discussion. This year's workshop also has another first. That is, it is the first time that we have significant participation from Yale NUS College. Dr. Stanislav Prislowski, a chemist from the Division of Science in Yale NUS, will speak on science education from the liberal arts angle. Professor Shafiq Adam, a physicist, also from the Division of Science in Yale NUS, will share his views during the panel discussion. We certainly look forward to vibrant academic exchanges and closer collaborations with our counterparts in Yale NUS. I hope that all of you will find the workshop interesting, beneficial, and enjoyable. Have a good morning. Thank you. Just in case you're wondering, I will give the welcome address, I'll chair all the session, I'll facilitate the panel discussion. So it is now my pleasure to introduce the first speaker for today. Our first speaker is Professor Alex Yip, and I think literally and figuratively, he needs no introduction. All of us know who is Professor Alex Yip. He's really an institution in our Faculty of Science. Like I shared with him earlier on this morning, in the late 90s, there was once he was giving a talk about his teaching practices, and I really wanted to hear about it. So at that time, I was the, I think, senior lecturer, just promoted to senior lecturer in the faculty. I make an effort, I took a taxi early in the morning just to listen to the talk, and I was totally blown away. And literally, I aspire to be like him, but I think I can still work harder in the next 10 odd years to come. And Professor Alex Yip has won numerous teaching awards, more than 20 of them. He was put on the honor roll of the Annual Teaching Excellence Award, the Faculty Teaching Excellence Awards multiple times. He's one of the very, very few faculty members in the university who has won the Outstanding Educator Award twice. In the old days, before we have this annual Faculty Teaching Excellence Award, the Faculty of Science used to have what we call the Distinguished Teaching Award. Now, the Distinguished Teaching Award, they only have one winner for the whole Faculty of Science, and Professor Alex Yip actually won it 3 times. I think we are all waiting very eagerly for Alex to tell us about how he motivates unmotivated science students in learning. So let's welcome.
Thank you. Thank you. Thank you, Sei-san, for the kind introduction. And thank you for inviting me to give this talk. And good morning, everybody. Today I'm going to share with you my experience of teaching in NUS. So the title of my talk is Motivating Unmotivated Students to Learn. But I'm going to tell you the history of it because I really know the history of the whole science faculty. I've been here 36 years, and I joined the Department of Zoology in 1982 as a lecturer. And during this 36 years, there were just high-speed changes. And I'm going to tell you all these changes. And I'm going to tell you what have changed, but there are some things that remain relevant, and we must not forget about that, although we are overwhelmed with all the changes. The first thing I want to share with you is what John Dewey has said many, many years ago. You cannot teach today the same way you did yesterday to prepare students for tomorrow. Isn't that true? Now, today's teacher need to have 3 knowledge domains. The first domain is content knowledge, which you all have. We all have. The second is pedagogic knowledge. The third is technological knowledge. Now, these 3 domains are very important. We cannot be overwhelmed by only content knowledge. And there are 4 important questions to ask. The first question is what to teach. Now, if you think about your teachers in the older days, they are in the instruction paradigm. That's why they focus on what to teach, and it's a subject matter. And that's why you focus on this domain, this red dot here, content knowledge. Now, I've been here 35 years. I experienced around 4 changes in curriculum. And most of the time it's in response to advances in research. Well, zoology and botany combined together, we change curriculum. Then later we combine with medical faculty, we have another change in curriculum. And then we refine upon that, and the most recent one was changing the courses from between second year and first year. So we have all these changes, but for some of the courses we teach, basically there's not much change. You know why? Because the half-life of those content are pretty long, especially for first year and second year modules. Now, but as teacher, we still have to change it. You know why? Because we have to change it in response to society needs. The society is changing to jobs availability, and especially for them to develop the skills, ability, and attribute so that they can feed the new job market. And those are very important things. Now, if we leave the instruction paradigm, we go into the learning paradigm. The next question to ask actually is how to teach. It's not what to teach, but how do we teach it? Now, in order to know how we teach it, then we must know how students learn. If we don't know how students learn, how can we know how to teach? Now, in this front, there are great changes, but are we aware of it? So if you look at this red dot here in the pedagogical knowledge, there were changes from cognitivism from the 70s and 80s to constructivism in the end of the 1990 and the early 2000s. And that's why there's a shift from instruction to learning paradigm. And then we know now students learn because they need to have actions, they have the learning cycles, and they learn interaction with each other, social interaction, social cognitions. And that's why now we have learner-centered teaching. Actually, there are a whole variety of teaching techniques we can use. For instance, small group teaching, thematic studies, case studies, problem-based learning, inquiry-based learning. There are so many. Now, that's purely based on pedagogic knowledge. How about we join it together? We integrate with content knowledge. Okay, then we have another type of thinking. And that's why Professor Limping in the 80s proposed that we have to teach tutorial. Small group teaching is so very important. And that's why suddenly we change all the infrastructures. We have built a lot of tutorial rooms. In the dean's office, there's one whole floor of tutorial rooms. And then because of action learning, active learning, it's very important for the student to have some kind of activity. Field trip, lab work, project work become very important in Singapore too. And then we have independent studies. And that was in the early 2000s. And then, of course, PBL is so famous in medical faculty, and we have one whole polytechnic purely based on problem-based learning. And that is a teaching technique we can use. But then how about the infrastructure? How about the timetabling? Are those not an issue? Can we accommodate that? And why then we remove all the tutorial room? What's the mindset? Why, when we look at our timetable, still 4 lecturing periods? Why is lecturing so very important? Can we remove it? Can we change the timetable? That's very important now because when we consider information technology, it really have changed the world. And if you look at the computer, PowerPoint slides, Excels, the internet, databases, Facebook, Instagram, more importantly, I foresee in the next 10 years, handphone is going to be very important with all the apps. Maybe you're familiar with Socrates, and all the equivalent. There are at least 9 to 10 software now. You can do all this interaction with the students. And then you can make your own lecture through Camtasia or equivalent, Adobe Flash, and of course NUS, build IVLE. We have webcasts. Oh, that is a big consequence right now. Because webcasts, even in my lecture, less than half the students will show up. How do you know that they're learning? How do you know how to use webcasts? Then how about assessment? How about IVLE forum? How do you use that? Again, then now you have all this. But how about your infrastructure? Why do we still have big lecture theaters? Why do we run out of space to run all these actions or activities? What about timetabling? How about the mindset of the people? How about the manpower support? All this activity, all this technology. Talk about PowerPoint slides. You know, when we started, that was at the end of the 1990s. We didn't know how to do it because we only know how to use overhead transparencies and visualizers. So NUS employs students to come to our office, talk to us, make slides for us. Each lecturer entitled to 2 2 lectures or 2 courses. And that was the beginning. But now to all of us, making PowerPoint slides is so easy. You need to have technical support. You need for people to keep track of what are the apps available, how to use it, how best to use it. We need to have study groups. We need to share all this information together in action. Awareness, it becomes so very important. If not, we are all way behind. Now, if you link pedagogic knowledge and technological together in this sector, you have something called the technological pedagogical knowledge. I even changed the learning theory from constructivism now to connectivism. We know it's so very important for students to learn how to access all this information in the internet, how to make all the connection, not just between database, but with people, with the correct people. It's very important, connectivism. Then it's game-based learning, so very important. Then you heard a lot about flipped classroom, blended classroom, web-based learning, and all this, whatever we can learn from these 2 sectors together without integration with content knowledge yet. But the problem when you go through all this thing now, how do you interact with the student anymore? You don't see them eye to eye anymore. You don't see the face anymore. They see a computer, you see a computer. What happened to the behavior? Isn't it very important for teachers to know the behavior of students so that we can influence them? Isn't it very important for us to impart value to them with human contact? Isn't it very important for us to motivate them? But now we have to motivate them without our direct contact with them. How do we do that? You see, there are 3 very important aspects of interactions in education. The primary one should be a student interacting with information. That's what we want to achieve in the lecture theater, in small group teaching. Also, that's what we want to achieve through internet. How do we do that? Well, the other 2 interactions, student-student interaction and student-teacher interaction. I think for a time, NU is overwhelmed by this. And then think about this as very important, this is important. No, this is the most important. You can have student-student interaction. They talk about TV, they talk about movie. What kind of interaction are there? You need the student to think about it. But it becomes hard because you're going through the internet now. So if you want to join these 3 together, content knowledge, pedagogic knowledge, technological knowledge, you're in this sector. And this is called the technological, pedagogical, content knowledge. Now you have all this at your disposal right now. How many of you are using them? And why not? Well, because basically there are problems. You will have problems. How about how to integrate with the content? The way you integrate this with content through engineering, arts, science, or even within science, between mathematics and biology would be very different. How do you integrate them is the point, so that you can enhance student information interaction. How to ensure learning has occurred. And how to judge effective teaching. How do you judge that? Is it anybody use this will be an effective teacher? Not true, because the student may not be actually learning from it as effective as when you use any other strategy. So to a teacher, you must have a basket of strategy, and you must know when to use what. And that's why something remain unchanged all this year. It's not just all this, but why would students learn? Now, if you know why students learn, then you would be able to integrate it successfully with pedagogical, technological knowledge. The first thing I want to point out to you is basically very important to all science students, curiosity. This is especially important for science students. Curiosity, simple curiosity is so very important. Einstein said the important thing is not to stop questioning. That is very true, very, very true. But why would people think and question? Why would they do that? They do that because even over 2,000 years ago, Aristotle said, human beings are curious by nature. William Arthur Watt said, curiosity is the wick in the candle of learning. It is true, because by now, we know there's something called psychogenic needs. And cognizance is one of the very important psychogenic needs. And I think that's what's driving you and I going after knowledge. Do research, construct knowledge. These are the intrinsic psychogenic needs, and from cognizance, they spring out curiosity. When you have curiosity, something amazing happens. An intrinsic need thirst for desire of knowledge. You want to process the information. Now, if you can instill that in the teacher, the students, something really, really amazing happens. You just need to present to the learner, the students, something called the stimulus. When you have the correct stimulus, external stimuli, provided by the environment, provided by the teacher, And especially when there are conflict between the stimulus. So here the word is conflict. You see, so if you don't use conflict, you can never capture the attention of the students. You just throw out the strict facts, and they get bored. And once you have the correct stimulus, and there's conflict there, controversy there, students will start questioning. They will develop questioning skills. Just like the father of classical physics, Isaac Newton, asked a very important question. Why would the apple fall? Just a simple question leads to very, very important theory in physics. Because you start searching for the answers. You start developing thinking skills. And then in your mind, you start developing a goal. I need to find out about this. And then when you decide on that, you have a desire, and you're thinking about, why am I doing this? What's the value? Education is about value. I think that's the most important point. Education is about value. And because they have a goal, they have a desire, the student will start exploring. That's why it's very important to have action and activities. Through this process of exploring, they develop reading skills, writing skills, manual skills, and affective attributes. This is so very important. You know why? When they do this now, they were faced with multiple choices. And they have to decide. There are multiple paths in front of me now. How do I proceed? And that's why they develop critical thinking skills. And because they will fail, they make the wrong choice. And they have to persevere. They have to understand failure are daily life processes. And when there is no path, they want to go towards the goal, but then they cannot find a correct path or appropriate path. What do? They think of a creative way. Now, that is how we want our students to develop creative thinking. They will develop a creative thinking skill, and they will take risk. Nobody had tried this before, but let me try. And when they fail, they just laugh over it and try it again. They develop humor. And these are all very important qualities of our students. And during the exploration, they need to talk to other people. They need to communicate face-to-face or through internet. That's why there's social interaction and there's social cognition. They develop communication skills, flexibility in thinking, cooperative thinking, open-mindedness, and also empathy. Isn't that very important for our students to have? How do teachers use stimuli? The very important thing is don't just give them one answer. Don't even tell them the answer. Tell them the unknown. Give them a puzzle to work on. Tell them about the controversy in science. What are the contradictions in theories? And all these are very important for our students because the teacher would then shift the student learning process from receptive mode to search mode. Now, once the student is in search mode, something beautiful happens. Something beautiful, really beautiful happen. Our students very, very often being criticized as they like to be spoon-fed. Why? Because it's the teacher who turn on their receptive modes. They start copying, memorizing, regurgitating. But once you start the search mode by using question, by using stimuli, the students start to think, to question, to reflect, to analyze, to evaluate, and to synthesize. Those are very, very important part of their development. And go back to this interaction in learning. The most important for us to achieve is for the student to interact with the information, right? And so they need to think about it. That's why they need to have cognition, they have the metacognition, reflection. And so the important thing is if you can use stimulus correctly, you can achieve those. At the same time, the student will develop tolerance of ambiguity, confusion, and contradiction. They will no longer just ask for what is the correct answer. They rather say, tell me all the possibilities, and I will explore. And at that moment, you know our students succeed. John Henry Clark said, a good teacher, like a good entertainer, first must hold his audience attention, then he can teach his lesson. That's very, very true. So when I teach my course 2231, it was used to be 1104, first year course, I break my lecture into every 20-minute segments. And even now when I use Camtasia to prepare for my e-lectures, I break it into fragments. More so important, as Seisong has said, the students nowadays have very short span of attention. So you break it into segments. And each segment holds by very intriguing questions. Can you hold your breath? How long can you do it? Do you know what's the world record? How long can you hold your breath? I bet you can. But can you hold your breath and commit suicide because you don't find life interesting anymore? Can you do that? Why you cannot do that? Using this as the lead question, this is called the anticipatory set, then I can set for the 20 minutes to tell them about respiratory control. What is a fever? When you develop a fever, what happened to your body temperature? Does it go up? Does it come down? But why would you feel cold during the onset of fever? You are having higher body temperature. But why would you feel cold? Then I use this to capture the student attention. Then I'll go into thermoregulation of the human body. So if you use this correctly, so induce curiosity, you can apply this to the internet classroom because you can combine with a content meta. So here is how I want to combine that with the content meta. Now, what does it say? Curiosity keeps us moving forward, exploring, experimenting, opening new doors, experimenting. That's very true. So once you start with curiosity, the student will want to explore. And that's why it's very important for a modern teacher to keep on thinking ways to get the student to do something. Because through doing something, they not only learn, they would have the fun to sustain themselves, to carry on learning. And that's why we know the very famous COPS, psycho-experiential learning. We all start with active experimentation somehow in life, in any event, not just in school, and then we have concrete experience, then we think about it, and then we abstract conceptualization through this experience, and go through a spiral again, and then we do experiment again. And that's why we know a lot about experiential learning, right? So, Ralph Tyler says something very correct. No change overall this year. Learning takes place through the active behavior of the student. It is what he or she does that he, she learns, not what the teacher does. This is really, really correct. We can prepare all the notes, we can prepare all the slides, but the student won't learn. The student can only learn when they start doing something. They read, they write, they debate, they argue, they question. And that's why when you just lecture, the students sit there, we all know that they can retain only 5%. When they practice by doing, they retain 75%. So instead of removing practical tutorial from the lecture, the module, it's very important for us to introduce not just even practical, we have to introduce more activities. And right now, with game-based learning, there's so much we can do. So now when we enhance not only a student information interaction through cognition, metacognition and reflection, we want to enhance student-student interaction through cooperative learning, social interaction through the classroom or in the internet platform. So that's why even in 2231, I have only 8 weeks because you share with another colleagues. I have a lot of things for the student to do. Very often in the beginning, they feel overwhelmed, but then at the end of the day, they fully enjoy it. They are reading assignment. I give them 8 monitor own learning to do. That means I don't bother. I just give them activity to do. They have to monitor their own learning. They have 8 weeks of Q&A. Every week there's Q&A. And the 4 mind map, they have to build a mind map. They have 4 assessment or misunderstanding of the concept they do. Whether how many they get right or wrong is not important. Just participation, I'll give them 1 mark. And there are 6 practical within the 8 weeks. And all these are designed for activity for learning. John Dewey say, give the people something to do, not something to learn. Very important message there. And the doing is of such a nature as to demand thinking. Learning naturally results. So the activity you design must demand the thinking, and learning will result. What's learning? Learning are changes that occur in the students' be it knowledge, skills, attitude, value. So presenting information will not induce all the changes. But you must interaction between information, thinking, and doing. And between doing and thinking, they must be linked up through learning activities. Doing must provoke thinking. How do I do that? Well, then I have to design all the tasks to make them understand through making connection. That's why the mind map. That's why the monitoring your own learning. That's why all this assessment. They start organizing the information, reconnecting them, integrate them, and beautifully, they start thinking about applying them to new situations. And because there is fun in doing all this thing, why? Because there's another very important psychogenic need, play and exposition. These are intrinsic psychogenic needs. When that gets satisfied, then they will feel the happiness and the fun out of it. And a very important thing is applying, transfer of learning to new situation, to real life situation, to society. And it is very important now, transfer of learning must be the ultimate goal of learning. They must transfer to the future space, future situations. So to enhance transfer, you can easily nowadays link it with web-based learning by introducing current issues, news resources, real-life problems, societal problems, just integrate with them. So the second point, when you want to achieve this in technological, pedagogical content knowledge, induce curiosity and create activities. Very important. Create activities. We have to forget about lecturing only. Then, of course, we have to stress on application and value. And this is especially important to adult learners. Many of our alumni are going to come back. How are we going to do it? How are we going to attract them? How are we going to make them feel useful? Encourage application then. Students are motivated to learn what is deemed as useful, not just for the grade, but for meaningful application in the future. Application is so very important. Again, in the 2231, I teach feeding. Feeding is so fundamental physiology. Every student must learn about feeding. So at the end of it, I will ask not only how do animals feed, can animal live without food, but any application. I will tell the students that, well, if you understand this little parasite here, which is a trypanosome, caused trypanosomiasis, the African sleeping sickness in Africa, then you can just stop him from getting the nutrients. Well, then you can prevent him from infecting other people, right? And so there's a value in learning feeding in trypanosome. Well, how about some other animal, while they're feeding, develop venom, like the snakes? Well, in the venom, there are a lot of goodies, a lot of bioactive substances, and scientists like Professor Kinney in our department can try to learn how to extract powerful painkiller from the cobra venom. How about why do we want to study animal that doesn't need to feed? Well, because someday we want to go space travel, right? And so can you imagine you stock up all the food in your space shuttle or your rocket? You run out of space. Isn't that nice? Nice if you can, like Sigourney Weaver, just sit in this or lie in this machine here and you can sleep for 50 years. Suspended animation is very important. Learners of all ages are more motivated when they can see the usefulness of what they are learning. And when they can use that information to do something that has an impact on others, especially their local communities, they become happy. They really want to do it. And this is especially important for adult learners. And now you know, and you has announced through the Parliament that we are going to help the students to enroll in NUS for 20 years. And they're going to come back. We have to develop a lot of courses. I think it's very important for us to really emphasize on transfer, application, and value to them. Why? Because there's a relationship between application and value. You see, when they go into your course, when they come to study under you, they are interested in it. There's no doubt about it. But interest is very self-centered way of looking at it. If you go through your course correctly and they can appreciate application, they will start developing, what's the value to myself when I do this, when I study this? And they start asking the question, what's the value to the others? And all this will change the motive, the attitude, and the behavior towards learning, toward other people, and towards the society. And this is very, very important. And that's why the third point I want to make is, if you want to go into this sector, you don't only induce curiosity, it's very important. You have to create activities, and you have to highlight application values. More importantly, at the end of it, there's another very important psychogenic needs. And they need to have feedback and success. And why? Because there's another need called ambition needs, through achievement, success, recognitions. Now, very many people get it wrong and think this is extrinsic. No, this is a psychogenic need. This is intrinsic, come within the person, if you know how to use it. Now, when you want to use it as intrinsic factor, as a teacher, you provide a smile, a nod, a praise, give them a good grade. Then, when you look at your student feedback, what do they describe you? Encouraging, inspiring, all this is the word describing you. But now, in the internet classroom, they don't see you anymore. That's the problem. They don't see you anymore. Then how? Well, very important. Student information interaction, I stress, so very important, right? Traditional classroom, teacher assessment is very important. But now we can use the internet classroom to have peer evaluation and also self-evaluation. And that's very, very important because Maria Montessori said the greatest sign of success for a teacher is to be able to say the students are now working as if I did not exist. If you're a good teacher, you make yourself redundant as soon as possible. You don't want to hold their hand forever. You want them to walk on their own. And that's why I designed assessment, not because I wanted to give them a grade. I wanted the student to do this assessment before a lecture, right after the lecture do this. Very simple question, 2 minutes. so that they can monitor their own learning. I also design assessment as learning, not of learning, not for learning, but as learning. So here is one of them. Misconceptions. I know they have misconceptions in prior knowledge. So I design assessment in such a way they just answer true false question or multiple choice question. At the end, I'll tell them which are the questions most of them get wrong. And then I explain to them through writing so they can self-learn. Very important. Provide feedback. Even when you're doing internet classroom, you have to provide them with feedback. So these 4 things, motivating students to learn, remain relevant all these years. Regarding whether you want to use flipped classroom, blended classroom, lecturing, tutorial, this remain the same. That's why Einstein said, I never teach my pupils. I only provide them the conditions in which they can learn, the conditions. Now the condition changed from lecture theater, from a tutorial room now, to the internet classroom. And actually, I personally believe this is a good platform to induce independent learning in preparation for lifelong learning. That's why I really want them to assess themselves or assess each other. Lifelong learning is so very important. Even the world leader want to talk about it. But how do you achieve it? You want to achieve that, you must give them motivation to do it. And the very foundational motivation would be curiosity. No doubt about it. Clay Bedford said, you can teach a student a lesson for a day, but if you can teach him to learn by creating curiosity, he will continue the learning process as long as he lives. That is the key word. And this is especially true for science, because curiosity is an intrinsic need, thirst, or desire for knowledge and information processing. And this is so important for our students. Many of students have lost them through our education system. But please, let's work together. Let's bring it back for them, because this is so very important for them. Thank you very much. Thank you. 30 minutes.
Thank you, Alex, for a really, really wonderful talk. I'm sure many of you are blown away as well. And I think I have to work very hard in the next 10, 15 years to learn from Alex. Okay, are there any questions? We have time for, one question. If you want to ask a question, please use the mic at the aisle, because we are recording this workshop so that this will be a resource for our faculty in the future. Yes, Stella.
Yes, any question, please?
Yeah.
Yes,
Stella.
Department. I have a question for you. You showed a slide on how you break down the assessment modes. There was a slide like you have a weekly assessment, MCQ for 8 weeks. My question to you is, how do you differentiate the better students from the normal students?
Okay, so in terms of assessment, there are different objectives. Okay, basically, let me explain a little bit to you. Assessment of learning is summative. Assessment for learning is formative. Assessment as learning is not for grade, not for anything, but let them learn through that process of assessment. So I'm using assessment outside CAs and final examination as assessment as learning. Remember, there's 3 modes now. Assessment of learning, assessment for learning, assessment as learning. But I still maintain CA. There will be 2 CA for that module, 40%, and then there will final examination 60%. So I use those for summative assessment. So in the sense that there are a lot of assessment. Now, but I have no choice but to separate this out, because only when the students forget about the grade that they can focus on learning. So I tell them, you just participate. I'll give you 1 mark. Okay? So they participate and they just focus on learning. When they get wrong, they have to find out, why did I go wrong? They don't pay a price for it. And that is assessment as learning. So to answer your question, how to differentiate them, I still go for CAs, official CA, because that's summative. And those are used for assessment of learning. I want to assess their learning, their outcome, what have they learned. And I want to give them a grade. And that I cannot run away. As responsible teachers, we always have to give them a fair grade. And that's why I would think that official assessment through CAs and final examination are very important. I hope I answer your question. Please, if you have another question, yes.
The reason why I asked you is, so when I went to law school, all of us, when we started with C grades, even though then we thought that it's a norm for us to get A. And we were in shock when we got C grades. And so in law school, they did the other way around. They shocked us, and then we worked hard, and then they gave us a B and A. Whereas over here, it's like all of us, we say we are A students.
Yes, yes,
and if we don't get A, it's the lecturer, it's bad.
Yes.
And so why is the difference? So when I ask myself, I say, what's the difference between law school and here? It's just different method of doing.
No, I think it's what you believe in. There are many theories about learning. You want to learn by conditioning behavior. You want to learn because you fear of failure, and that's why you want to do it. Or you want to bring out the best of the mind and the heart of the students. So they do it because they really enjoy doing it and because of the psychogenic needs. So my starting point is, within the psychogenic, there's one is called fear. So you want to play down the fear. To me, okay, I'm very sorry, I want to play down the fear. But I want to play up the other psychogenic needs so that I make them positive. I don't want them to do it throughout the whole life because they're scared, or they fail, or they don't want to fail. I rather want them to think about success and how do they make them successful. It's only a way of thinking. So I think all depends on our community now within science faculty. Yes, law has their own way, but what way do we want to have? What do we want our kids to have? What do we want our students to have? Positive thinking or fear because I get a C? I think that's something for you to ponder and for you to decide on.
Thank you.
Thank you.
Thank you.
Thank you.
Let's thank Alex again, and he'll be back in the discussion panel, and you can ask more questions to him later this morning.
Okay, and now I have to plug my... Yeah, it's fine.
Okay, our second speaker for this morning is Dr. Stanislav Prisovsky.
Thank you.
Okay, thank you. And from Yale NUS. And as you know, that Yale NUS, the curriculum is completely different from what we have in the Faculty of Science. And Stanislav actually got undergraduate liberal arts education in chemistry and physics before doing a PhD. And after he has done his PhD, he did a postdoc in the University of Eindhoven in the Netherlands, and interestingly, 8 months with our friend in Jurong, NTU, before joining Yale NUS. And this morning, he's going to tell us about the liberal arts and sciences curriculum in Yale NUS. So let's welcome Stanislav.
Okay, good morning, everyone, and thank you for this kind invitation. It's quite nice to come as a child to one of the parents of Yale NUS College, namely NUS. So today I'll talk to you about the liberal arts and sciences, and in particular a small case study of a course in which I've been involved last semester. And it's actually great to see that even though we are the latest kid on the block, like we're just a continuation of a trend of education and excellence in Singapore and NUS over the years. So for those of you who haven't been across the road in Newtown, this is Yale NUS. This is actually the schematic of Yale NUS before it was actually built. This is Clementi. And it is a residential college. It is somewhat inward looking, some might say. On the outside, we don't have any big signs. We don't show off. I don't know why. But the thing is that the campus is open. So please come and visit us anytime. It actually could be quite a relaxing space. We're a semi-autonomous university, college within a big university with another university connected to us. So it's a complicated relationship. And I will explain to you some of what we're doing. There's also a bit of a confusion because some of our labels would call Chendana Residential College. These are residential colleges. The students live in those tower blocks. These square structures here are the dining halls. And each residential hall has a courtyard. There is a central big courtyard, and all of them are open to the public. Now, this is actually a picture I have taken from our admissions office. There are some trees. Some of them are the only one of its kind in Singapore. But the place is not just the building and the nice trees and the lawn. The place came to be it has a vision. And the vision is a community of learning founded by two great universities in Asia for the world. Right? So that's something that the first president had in every single speech. So I wanted to deliver it to you and maybe, move on. We have a mascot. It's a small bird, just like how we are. We are a school of less than 1,000 students. And it's a yellow-orange, it's a orange-blue kingfisher, which has a Greek name, Halcyon. Now, a little bit more about the brick and mortar. So it is a relatively small campus. It did cost a lot of money. And Yale NUS as an institution, as the vision and the mission, was established in 2011. It welcomed its first students in 2013. Initially, they were in RC4 for 2 years. And then the campus was built in 2015, and that's when I joined after my short stint at NTU, Yale NUS College. Right now, we have a little over 120 faculty, about 120 staff. And I guess the big difference between big universities and small liberal arts colleges is the very small student-to-faculty ratio. It is 8:1. And something else which is quite amazing, actually, for me, somebody who has gone to, as an international student to a liberal arts college, is that 40% of our students are from abroad, are from outside of Singapore. 60% are Singaporean or PR. So this is actually a very high number. In the US, if you have 10 or 12%, you put it on the front page of your admissions brochure. And as you can see, our first class, which we just graduated in May, was a little over 150. It has grown, and eventually it will reach about 250 students per cohort. Now, other than a vision, we also have a mission. So the mission of Yale NUS, something that really drew me to look into Singapore first, and then discover all the great science and education that's going on in the whole island, not just at Yale NUS, is the following. So the mission of the college is to redefine liberal arts and science education for a complex, interconnected world. So we not only want to do something that has been done before in ancient Greece or in the US, but we want to redefine it. We want to make it new. We want to make it relevant. So if we want to redefine it, maybe we need to define some terms. Liberal arts and sciences. So actually, I have a question for you. Does liberal arts education teach you the sciences? Is sciences included in liberal arts? I haven't given clickers, so maybe I can do a little voting. If those who think yes, maybe you can put a thumb up like that on your chest, so it's semi-anonymous. Okay, maybe you guys are very confident. If no, you can do that. So does liberal arts include the sciences, something that is being taught in the Faculty of Sciences, chemistry, physics, mathematics? So can you please vote? I just want to see roughly. Okay. And, oh, wow. Okay, and who thinks that it's not? No? Okay, well, good. Okay, so the voting here wins. So liberal arts, at least the way it is defined on Wikipedia and in many other books, is it originates from ancient Greece, in which the free men, it was only men at that time, so actually, the people who say good old times, it was not all that good in the old times. But it was deemed that a free man has to be able to handle himself well in society. And in order to do that, they had to master the trivium, which is grammar, logic, rhetoric, and the quadrivium, 4 things: music, arithmetic, geometry, and astronomy. Not included in that, but very important, is martial arts. So as somebody who grew up in Eastern Europe, I always associated martial arts with Asia, but even in Europe, you had to survive in order to go and practice your oratorial skills. So they did martial arts as well. So as you can see, even in those old days when we did not define science as the scientific process, as what it developed in later, geometry, astronomy, I mean, we can recognize science. So liberal arts in the US in the beginning of 17th, 18th, well, maybe 18th and 19th century has evolved into a system which is quite recognizable from specialized big universities in which you enroll directly after your secondary education and you go into a specialized field of whatever profession it might be. And the 2 distinctive features would be distribution requirements that give you the breadth of knowledge. And then you also have a major which you have selected typically in your second year, that provides you in-depth mastery of a field. So the breadth is not at an expense of a depth. You just have to go broad in order to realize where your true intrinsic values lie, where your interest, where your curiosity will drive you, after you have actually tasted a little bit of the various fields, and then you go very, very deep. Now, what do we do at Yale and US College? So at Yale and US College, some of those characteristics of the liberal arts education are well recognizable. However, instead of giving students too much freedom and telling them, look, take any courses, it has to be 1 math course, 1 science course, 1 humanities course, we say we know better. And we don't really know better, but we have come up with this plan, and maybe the forefathers before I even joined. So Yale and US has a common curriculum. There are a few places in the US that do that. University of Chicago, I think, follows that common core. And it consists of 10 courses. So these are courses that all students must take, and that builds also a sense of community. So it's not that one person takes biology, another person takes astronomy, they never talk to one another, they don't have shared experiences. Here, all the students in their first year must take literature and humanities 1 and 2, it's a 2-semester sequence. Philosophy and political thought, PPT 1 and 2. Comparative social inquiry. And then in the sciences, quantitative reasoning, scientific inquiry 1 and 2, modern social thought, and then historical immersion. So this is the common curriculum, which is somewhat unique to Yale and US. Now, in order to wean students off the grade, so the grading came in the previous question, Q&A, the first semester is completely ungraded. So we give them grades, but they do not feature in the transcript. But I have to say, in the second semester, students become quite anxious again. So it does show up in the evaluations a lot more. So you cannot undo what education systems around the world, not only Singapore, have been doing for 12 or 15 years prior to that. Now, the majors are deliberately small, so they consist only of 9 courses and 2 semesters of capstone research. And that allows you, it's a 4-year program, so in total like 32 to 35 courses for the students who overload, and they always do somehow, you have plenty of electives. Now, one can decide to use those electives to get a minor. We actually do not allow them to do a double major, something that I did in so I'm guilty of overloading in college, so I did physics and chemistry. Here we tell them, no, you have to contribute to the community, to the society, by being available. You cannot just be mugging all the time or sleep deprived. And this is an important part of the residential life. And many students take language courses as part of those electives. So they can have a major and a minor, or just a major and then take all sorts of classes. The fact that this major is small comes with its challenges. because again, some of our students in the sciences want to go to graduate school. So clearly they're anxious about how their application form is going to be received, how their CV is going to look. And yeah, then we tell them, well, look, if you want to go to graduate school, then you have to use your electives well. Now, but today I'm going to talk actually about the science in the common curriculum, because by and large, myself and the colleagues in sciences, we make the greatest impact when we teach in the common curriculum, because everybody has to take the common curriculum classes. So I'll give you a minute to read the abbreviated course descriptions for the 3 courses. Quantitative reasoning, they're taken in a sequence. Scientific inquiry 1 and scientific inquiry 2. I'll give you a minute, and I will then ask you if anything interesting comes out of that. Like, do you notice anything that's strange, different from NUS? Because honestly, I haven't been to NUS, so I don't even know if we're all that different. It's difficult. A minute of silence is difficult. I don't know if many of you teach. It's hard. Did everyone have a chance to skim through? Yeah? Okay, so does anything stand out? Anything that is markedly different, markedly wrong, exciting? So this is a different setting for me. It's very big. I don't know the people. We did a cultural awareness, so maybe I'm more of a direct type. I don't know if people are direct. Some on the front are definitely. So, anything? Do those sound like, those descriptions sound like science courses at all? How do they appear? Maybe what's your feeling? Sorry? Okay, so light on content knowledge. And in effect, we even define it here. Indeed, that is true. We say the goal is not to acquire specialized knowledge. It's very curious, right? We put the word not. We define the course in a negative. Indeed. Anyone else? Will they trigger your curiosity? Do you think it has a chance? So we have great aims, right? The course aims to develop a deep appreciation of scientific thinking by tackling a question that is still under debate. So this is the debate and conflict that we just heard about. Right? And even we say that this could change from year to year. So this year we'll focus on climate change and how we know that global climate is changing. Right? In the future, we might choose something that's actually a bit more contentious, because at this point, everybody has watched many online materials. So there is groupthink to believing that climate change is real. We have caused it, and there is no debate. Yeah? So when I said liberal arts and sciences, practices, and in a sense, these are our hopes and aspirations. So I cannot say that that we're hitting all these marks. And we've been around for only several years. And this course that I'm talking about has been offered only one semester. Why? because for the 3 years that I have been here, every single semester we have innovated. Every single semester we have tried to tweak things. So Neil, who is sitting there, and I, we have butted heads in many committees on how to improve the common curriculum. And our faculty, actually, Neil Clark, he had taught in quantitative reasoning, scientific inquiry 1, scientific inquiry 2, and their predecessors. They were called Foundations of Science, FOS. Yeah? That was the time before we had a campus, so we took the FOS bus to here. So it was cool to do some soap making. Yeah? So how do we do it? Right? It's about people. So a mathematician, a chemist, a biologist, and an ecologist walk into a bar. Right? It's almost the beginning of a joke. But this is our team. So the course coordinator is Hui Kun. Some of you maybe know her. She's in CQT. Kiat Hua, who is also in the audience. He's a chemist. Morris, he's a life science. He's a biochemist, computational biochemist. Actually, it was the connection between mathematics. Stephen Pointing, environmental studies. That's me over there with some molecules in the background, balloons. These are advanced teaching aids, environmental studies, mathematics, life science, and chemistry. This is our teaching team. And we have to come up with a cohesive curriculum that we can deliver, we can develop, and try to hit our marks. So when the students complain that, oh, teamwork is so hard, I'm like, yeah, I know. Teamwork of 4 is hard. Imagine 8. And we didn't have that training ever before. We were scientists who were digging into one particular thing. But the world is becoming more and more interconnected. So actually, it's been a great humbling experience. Now, this is what we came up with. So after there was a common curriculum review, this is how we decided to fix all wrongs with the previous iterations of the courses, the second course of the common curriculum. Notice that it's quite complex. But what we have is we have this section, CE, Common Experience, which brackets some green section in the middle. Right? And from the very beginning, the college was struggling with having a common curriculum, telling students, here is what you do. And we saw that at some point it was not working. They could do it for one course, second course, but then by the third course, they're saying it's not relevant to me. Maybe it's relevant for 10%. Maybe you've picked a great topic, 20%. But it's not relevant for everyone. So then we went the other way. We almost went to distribution requirements. There were all these half courses the students could take, but then the commonality was destroyed. So what we have come up with, and again, maybe we're going to recycle this in a couple of years, or recycle, I mean throw away. But right now, we're trying to do a little bit of both, a hybrid system. And the hybrid system consists of the following. For the first 3 and the last 3 weeks of the course, the students go to the same lecture, and then they have seminars in which they discuss the same topics with the instructors that that I showed in the previous slide. And the question we have chosen is the climate change. So at the beginning, we introduce them to some basic questions and statements about climate change, and then at the end, we ask them to work in teams. So in teams, they have to work on a project together and bust the climate change myth. So they have to choose a myth, show that it's a credible myth, they didn't just make it up, and then bring various scientific evidence, figures, arguments, create a poster together, and also individually they have to create a frequently asked question type that addresses this issue. So there is individual assessment as well as group assessment. And then in the middle, we squeeze in something which we call deep inquiry, or deep inquiry, if you prefer the British pronunciation. And in that one, we allow students to make some choices, to feel empowered. So they have these DI 1, 2, and 3, which deal with specific inquiry modes. So again, this is not about particular content knowledge. I want them to know bond vibration. It's about measurements and data analysis. Another one is modeling and simulations, and then DI3, effects and impacts. So now you can see how our faculty would naturally split. So Kiat Hua and I, the chemist, we were here. There was a physicist also could have been on our team, but for that iteration it wasn't. Modeling and simulations, these were the computational people, and the physicist, the mathematician was there. And then the ecologists and the biologists were in the effects and impacts of climate change. And the course coordinator did something very smart. First, we formed the teams. So the teams were formed, 6 people. And then the team had to delegate among themselves which 2 people will go to each of the DI 1, 2, and 3. They could also trade between selves. Because at the end, the team will come back together, and there will be representatives who have gone to DI 1, DI 2, and DI 3, and they will work together and teach each other. Because that's when that's research has shown, and we've seen some evidence, that's when you learn best, when you have to explain it to somebody. Of course, there is the issue of freeloading, but even that, you can say it's a transferable skill of knowing how to deal with freeloaders, or actually how to freeload. I mean, why does everybody have to work all the time? If somebody has to, like, you know, people like to work, okay. Other people like to be carried around. No problem, right? So that's at least how I rationalize it. Okay? And in the DI1 that I was the coordinator for, that Kyatwa and I came up with, these are the topics that we talk about. And again, they're not etched in stone. Next year, there will be another person, a physicist, joining our team, so we might tweak it based on the feedback. So these are the topics that we deal with each week. What does this is the International Intergovernmental Panel for Climate Change report measure. And this is our way to introduce some simple constituents of matter. So here is about the content. So this is another tension that we have. We want to teach the modes of inquiry, yet if you do not ground it in anything, then what are you describing? Then you're at some very high level in which for educators, maybe it's okay, but for students, what do they measure? So that's when we introduce atomic structure of matter, covalent and ionic bonds. Then we talk about how we measure matter, spectroscopic techniques. But that means, how does the machine know when I press a button to display a number which means something? So oftentimes it's by shining light through it, right? And because people have heard of acidification, and that's introduced at the beginning, we also introduce chemical equilibria. Now here I've given the percentages of the different assignments. So they have a midterm exam that they can sit. In the past, we've also had an oral exam, individual. Our class sizes are about 18 to 20 students, so it's possible even to do individual oral exams, which train interview-taking skills. But at least the experimentalists in the team will also believe that one does best if one is in a lab setting. And even though some students have never been in a lab, some of them did not even know Yale NUS has labs, we brought them to the labs, and they get to make their own measurements. And they had to make a direct measurement between pH and a color of a dye, and then the next day, they had to do, the next section, they had to correlate a color with pH. So they had to do indirect measurement of the effect of CO2. We had dry ice into the water to change it, right? Then they wrote a lab report based on that. And in all of that, they collected the data themselves. They had to deal with uncertainties, error propagation. How do you even plot things? Many of them we talk about nowadays, kids have access to apps, to phones, and oftentimes they don't know how to use them accurately. And I encourage cell phone use in my class. Like, if you don't know anything, check it. But they're even afraid to check, and this is very strange, because the phone is just for looking at cats and rating pizza. It's not for looking up molecules. And even though we like to praise our students, we're very selective, the top 5% only get in, the kids are kids. I mean, we're the same too. I mean, even here, all of you are sitting in the back, similar to how our students sit at the back, right? So this is not something that is a generational thing. So these are some of the other things that this DI used. We had weekly ungraded assignments for challenging questions that involve thinking. You had to submit a photo of whatever your scribblings, derivations, or thoughts about the issue are. And then we would solve them in class. We used interactive simulations. So even though going to the lab is amazing, oftentimes when you go to the lab and you drop something, so many other things happen. Never mind somebody is poking you, or you're taking a selfie because you're wearing goggles. So there's so many things happening that actually the students do not tend to focus on what you want them to focus. Well, thanks to the power of the internet, we have these online simulations in which you can actually shine a laser and see what happens, or shine white light and see how it splits into color. Then they had to do their own data collection and data sharing. So this was something that they were penalized for if they didn't upload their data on time. And everybody for their lab report had to actually use not only their data, but the whole team's data, all 72 of them. So they were like multiple sections, we all combined the data. And 2/3 of it was thrown away. It was badly collected, and they had to make that call. And they would say, Prof, which one should I throw? I'm like, well, this is the assignment. That's what you have to do. Okay? So here is a simple, this is a sample extrapolated a figure in which we have pond water, seawater, ultra pure water, before and after a piece of carbon dioxide, dry ice has been dropped in. So then they have to make a hypothesis, have to think, how come ultra pure seawater and pond water react differently, even though they roughly, first of all, seawater is a bit alkaline, but these two start at the same pH, but they go down differently, right? Something about buffer capacity. Okay. And in the overall structure, so at the beginning we were introducing, so again I have to go back and forth, is the basic things about climate change, building scientific understanding, and actually here in week 2, we did a simple simulation of Earth as a black body. And interestingly, yeah, temperature to the power of 4, it's a difficult equation. Even for the students who later became our science majors, they would make calculation errors. And we solved those equations on the board. Right? The teams had to make a proposal of what they will study, then they split into the DIs, and when they come back, they have to synthesize their arguments. They had a chance for a debate among different teams, and they had to create a report, individual FAQ essay, and a team poster. So here is a sample poster. So this is in a team of 6. So clearly I have chosen one of the better ones. This is very infographic heavy. Some of them are very science heavy, like research papers that have been, the raw data has been plotted. Right? So this is the myth here is animals and plants can adapt to climate change, right? Because we talk about bioclasses about evolution. In SI1, they talk about evolution. Well, how come it's so dire now? You know, the dinosaurs died, okay. So what if some elephant died? Well, why is the big deal? Okay, the koala, okay, we'll save it in the zoo. Right? And then the first impact. So this is the part where I leave open and we have to study this, and we have promised to ourselves that in the next 3 years we will not change the common curriculum. We're going to see how we can improve it before we redesign it again, so we don't change too many variables. But these are the first evaluations that I want to share with you. So very open. So this is for the whole SI2. So the professor helped me understand concepts around 4. Challenged me to actively engage, close to 4. I'm motivated to explore beyond the material encountered in the seminar. Okay, this is close to neutral, right? So this is some area, to me at least, of concern. I found it easy to obtain feedback, and seminar professors was valuable. Again, this is low-hanging fruits for us when we have few students. I know you deal with classes of 300-400 students. It's a lot harder there. I mean, I'm running out of time, so I don't want to ask you, like, what's wrong with this figure? There are no error bars, right? The error bars are about ±1, right? But this is actually how the software outputs it. I can see, based on my own evaluation, it's about ±1. But I have to say that, you know, I have to be, like, honest with you, since our first meeting. Our Scientific Inquiry 1 and 2 and QR have statistically significantly lower scores than the humanities and the social sciences. Now, there might be multiple reasons for that. Again, there might be misunderstanding of what liberal arts is. We're not drawing enough students. So that is one of the possibilities. So among the 14 majors, as well as this double degree with law, so we have a total of 200 students, 22% are in the sciences. So this is the mathematical, computational, and statistical sciences, which is the second most popular major after philosophy and politics and economics. And then we have physical sciences here and life sciences here. Some students say maybe you should combine to call it natural sciences so the bar is bigger. Yeah. So that might be one of the things, and we're doing lots of outreach. We try to go to science and engineering fair in order to change that conception of what liberal arts is. That you're taking all these things and you can become a greater scientist because of that. And you can interact with people who later will be in various fields and will make it easy, allegedly, to garner grant money. So with that, I would like to acknowledge Hui Kun, who is the coordinator, Kiat Hua, who is my partner in crime for DI1, Shafiq Adam, who has been my mentor at Yale and US, and SI2 students. And you for your attention. Thank you. Questions, comments, concerns?
Yes, questions for Stanis? Anyone? Don't be shy.
Oh, there will be a panel discussion later on, but
so
I can take at least one question.
Maybe I'll just ask one question.
Okay.
Yeah, I noticed that for your scientific inquiry, you have a team of colleagues from different disciplines teaching the same course. And usually if you have a team of people teaching the course, there's a tendency that each person will just do your own thing, in the sense that sometimes, you know, sometimes in terms of team teaching, like this person is responsible for, let's say, this topic, the few lectures on that topic. So how do you integrate everything together seamlessly? Because I'm sure you have done a certain amount of integration.
Yes.
But your team is big, so that is quite challenging. Yeah. So we would like to hear this.
It is, and seamlessly, we're still working on it. It's a work in progress. If you read the evaluations, it doesn't seem to be perfectly seamless. What we do is we actually spend a lot of time in meetings, in discussions, in debates. So it is exhausting, but at the same time, it's exhilarating. And it's an opportunity to learn. Speaking about lifelong learning, this course is not a climate change course. If it was, it would be easy. We just watch some online video about climate change, we'll be able to deliver it, or at least fake it enough. But we have to come and make it our own. So then we have to teach each other, question our notions of what significant is. Even like when biologists, chemists, and physicists talk, the jargon is different. So, I mean, I cannot say that we have arrived at the solution, but there is lots of discussions, and even though one person might deliver the lecture, we have all agreed on the content that is delivered. But to mitigate part of that, we have the DI, we have the DIs. When actually the teams are smaller, what you teach is closer to your specialty. The evaluation showed that students pick up on our passion is greater when I talk about bonds of carbon dioxide, rather than carbon dioxide destroying some mollusk. As in, I know it's important, but intrinsically, I cannot have the excitement to bring it forward, right? And that's a tightrope that we're trying to walk.
I see. Okay, let's thank Stanislav again.
Thank you.
So we'll break for tea. So tea is served outside. So please be back here at 10:45. Thank you. Ethics project. So he has actually done practical work on data analytics, and as a result, he's also the deputy director of our data science consulting center. So today he's going to show us about learning and then teaching statistics. So let's welcome Vic.
Hello. Okay. Hey. Hi, everyone. So I At the beginning, Sesong said that I'm here to give you the point of view of the new person, right? So because I'm social media savvy and all that, but actually I'm not. I don't have a Facebook account, I don't tweet, I don't have a data plan for my phone, but I'm no Luddite, okay? I do use technology, but what I'd like to share today is just some personal reflections, like what the title says, okay? I'm just a new guy. These are just some observations. So bear in mind, it is a sample size of 1, just my personal reflections. What happened to me 20 years ago, and what's happening to me now, okay? Okay, so... Okay, I will just hold it. So this is a further underline, okay? So what I did was, I tried to think back what happened to me when I was an undergraduate here, and I tried to list down what my experiences were. Remember, it's just personal ideas. Some of you may agree with what I say, some of you may not. Feel free to tell me. And then I will tell you a bit about what I'm doing in my classes. Again, the point is not to tell you how amazing my teaching is, because definitely it's not. It's just to share some ideas. If you can tell me how I improve, or if you can tell me there's a big gap in what I'm doing right now, please tell me. I just like to learn from you, okay? So remember, whenever someone this is a point of view, right? I don't have data, I don't have plots, I haven't conducted a survey, it's just a point of view, okay? Okay, so I studied in NUS from 1997 to 2001. Our department, our current department where I am now, the stats department, just celebrated 20 years. So it started while I was a second year, but I matriculated in the math department, so I got a degree from there. So let's go back in time and try to think about, let me recall to you how it was for me to learn. So what we did was, we would go to class, and then the instructor or the professor would write on the board or on his OHP, and we would copy notes, and he would explain things. And they were very clear. We understood the structure and everything. But I spent a lot of time internalizing material on my own. Right? I would go home, I would read the notes, I would go to the library. I was very excited to look up different books to see different definitions of the same thing and how they're all equivalent. So I had to do a lot on my own. We never had group discussions in class. In tutorials, it was about some professors would give us the solutions. Some of them would ask us to go up to the board, and then we would have to go up and try and see if we could get the solutions. But we never broke out into groups to discuss things. So again, this is personal experience. Maybe even then, I was a little bit antisocial perhaps, so I never got into the groups. Maybe my classmates were there, but right? So I never got into groups. We were never asked to do discussions and present our findings on anything, right? It was all about understanding the material, solving some problems, maybe making some proofs. We didn't have to spend time doing cross-faculty modules, right? I didn't have to go all the way. I think this started in my 3rd year, right? So my juniors, they would have to ballot. They antagonized over what courses to take in the arts faculty and what the timetable was and how many girls would be in this class. But I didn't have to worry about all that, right? So I just took the science modules. The only general class that we took was the HR class. We covered Maslow's needs, that one, right? So that's the only common class that the whole university took. Closed book exams were the standard. I still remember there was only one open book exam that I had. It was on logic. And I still remember, even though it was open book, I memorized a lot of things. I still remember, because of that, I know how to prove statements are false or the contrapositive, modus ponens. I still remember all that. But during that exam, it was open book, so I brought in the textbook. I didn't open it even once. I just didn't know where to look. The questions were so difficult, I flipped through a couple of times and I just stared at the exam blankly. So there was no use in it being open book for me, right? And that was the only one. We never got solutions given to us to past year exams, to past year tutorials or current tutorials. No solutions are given out. So sometimes, if I wasn't quick enough to copy the solution, when it came to exam time, I wouldn't have the solution to a particular problem, so I would just convince myself, I'm sure this won't come out, and then it would come out, and then, right. So we had to copy notes by hand. Okay, so nothing was given out. Now, okay, so I haven't come to now yet, right? So there were times when, right, you know what happens now, right? And this was pretty much the same way I learned in graduate school about 12 years ago, right? The professor would go slowly on the board. There was only one professor who gave me printed notes, and we still have that. But even then, he had the printed notes, and then he would still write everything on the board and go through it slowly with us. And one of my advisor, right, he would say that when you copy down things on the board, what you're writing goes through your pen into your body and internalizes into you, right? So I feel like that pace is different. Now it's just too fast the way we go through. But there are reasons for that, and I will give you my opinions on the reasons for that. Okay, so these were my experiences. What do I remember learning? So that was how I learned, or my feelings when I was learning them. But what exactly did I learn? So in statistics, I remember we did a lot of theoretical or math stat. So what we call, so this is, a lot of the terms I use will be statistics-centrics or what people say today, data science-centric. So if you don't understand, please just tell me I don't understand what it is and I'll tell you. So math stat means that when we do statistics, we focus a lot on the mathematics behind it, right? The formulas for the distributions, how this distribution can morph into this distribution. At the back of one of the textbooks we use is a map. From this distribution, what conditions lead you to this, and what special conditions lead you to this. And this is a special case of that. And that was an amazing mind map of all the distribution. So we focused a lot on these techniques, right? We really got down to the math. I didn't do any coding in any of the modules, not a single one in the stats modules. The only time I did coding was when the CPA minor just started around that time, and I took up that CPA minor. So we learned C, we learned Java, and that's the only place I did coding. Okay, but I'm thankful I was exposed to it because I really like coding. Right? So if you ask me to go back in time, there is a high chance that I would take computing instead of statistics. When I was making that decision back then, I thought that you needed a computer to have some knowledge of computing to get into the computing school. But I didn't know everybody started from scratch. But in any case, we didn't do anything. The first time I experienced the internet was in my second or third year. First year, yes. That's the first time we get an email account and then we go on the internet. Right, there were fewer topics than now. So I feel this was to an advantage because we were able to go deeper into each of the topics. For instance, when we did time series, we just went through an old textbook by Box and Jenkins, and we went through this big class of models called Mcmc Models, and we didn't do anything else. Okay, so fewer topics were covered. So here's the current context. In the last 5 years, so I've been here for 5 years, and here are the things that I've taught while I was here. So probability is a first-year class. Right, probability is a first year. There's a big bunch of students who take it from engineering. It used to be industrial engineering as well. Our own stats students take it, and those who are doing a minor take it as well. So it's a big class. I feel it's tough for them, okay, because they see it in their second semester. It's a huge shock for them. When they learn about probability in school, they focus a lot on combinatorics. When they come here, I stress to them, combinatorics is a really, really small part. When I teach them, I make them realize that probability is about decision making. So I'll tell you more about this, about how I do it, not, okay, later on. Then I taught the statistics for life sciences. This is a second-year class for those in DBS, you know. So if your students tell you they took this class and you are surprised at how little they know, I'm the one to blame, okay? I feel like we could have done a better job on, I could have done a better job on this. If I do it again, I have some ideas. Okay? So second means second-year courses. Okay, and then visualization. Now this is a topic that didn't exist when I was a student. Now it is a discipline in its own right. There are jobs, data visualization expert, right? And I'll tell you about this later on. I taught simulation. This is a third-year course. This one I cover how to generate random variables, how to run discrete event simulations, and so on. I'm supposed to end at 11:10, is it? Okay. 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 Then I taught applied time series, and then spatial statistics. So here are some conclusions from what I see the students who experience these classes. So first of all, some observed differences in terms of the topics we cover. Now, coding and programming are the cornerstone of every class that I teach now. If there is a class that doesn't involve programming, the students get really disappointed. They feel they're not learning anything, is what the impression I get. So all the classes here, I use coding except for probability. So probability is a very theoretical class, so there's no coding at all involved in that. But in all the others, they have to do a lot of coding. Now, the statistics for life sciences, we use SPSS. Right, so if we do it again, maybe I'll do something different. But in these four, it's heavy on coding right now. Previously, when we taught the classes, we focused, or when I learned the classes, there was a lot of focus on confirmatory analysis. So you collect some data, you build a model, and then you test for the effect sizes. Is this a significant effect? Is this associated with the response? There was a lot of study on the models, on the statistical and inductive logic to do that. Okay? Hypothesis testing, Neyman Pearson, the p-values, we covered a lot of that. Design of experiments, right? Fractional, factorial, all those experiments. And asymptotics, the distribution of statistics as n goes to infinity, so that we can perform a hypothesis test, so that we can find a confidence interval. So there was a lot of focus on this. But today in the classes, there is a huge emphasis on predictive modeling, right? How can I forecast 1 week later? How can I forecast if a new observation comes in? What is my forecast? What is my error on the forecast? Computational procedures. If you teach them a model, you have to show them how to do it on a computer with R or with Python or something. Otherwise, it's not useful anymore. And knowledge discovery, data mining, right? So we're digging into the data, finding more patterns, recognizing unseen significant effects or outliers or whatever, okay? Unexpected. Okay? So the focus is on this nowadays. In terms of the topics that we cover, mainly because of the computational increase in power, we can Mcmc models, these are Markov chain Monte Carlo models and Bayesian models, they're more accessible to people. There are just packages that you can run. All you have to do is specify the model in some graph theoretic language, and you can get the output. So it's much easier for people to do. You don't have to figure out the mathematics behind the distribution or how to sample from it. These models didn't exist when I was in school. Or okay, random forests. Neural networks were around for a long time, but they didn't become accessible until recently. Once the backpropagation algorithm was solved. Okay? Random forests, Leo Breiman came up with it in, I think, 2000, something like that. Okay? So these are new models that people have to learn. Path models. When you have survey data, one of the most intuitive ways to analyze it is using a path model. So this one uses partial least squares. So nowadays, this is very widely used. In time series, instead of just ARIMA, there's a whole new family of models called exponential smoothing models. They've been put into a proper state space framework, so they are legitimate to use. You can get confidence forecast intervals and so on. So there are many, many more new topics for students to learn today. So this is another one of the differences that I've observed. They don't have the luxury of focusing on just a few models and going deep into them. Another thing is this. There is a huge amount of educational material available online. So you all know about Khan Academy, right? We even point our students to it. In calculus, in the probability, if they're not sure of calculus, they go, I tell them, take a look at the Khan Academy video. Data Camp, have you used this? So Data Camp is an online website for people to learn R, Python, SQL, and they're adding more and more languages all the time. And within the university, if you have if you email them, they'll give you open access to it for your class. So for the entire semester, all your students can go through all the Data Camp classes. Okay, so I use, so they can get this online. They can get this, I think $30. For $30, they get full access to Data Camp. And it's only a matter of time before VIP Kit turns to tertiary education. Have you heard of VIP Kit? So VIP Kit is a really, really big startup in China. Almost as big as the one that beat Uber, TT, I think. So this one, what it does is, you enroll as a tutor, and you do one-on-one tutoring through the computer to kids. It's expensive. So for the rich parents, they pay, and their student gets one-to-one tutoring. They don't sit in a class with 40-to-1 ratio. But right now, it is until high school, but it's just a matter of time before it goes to tertiary. I'm sure they have it in their plans. Okay? So the question arises, what's the use of me? I struggled with this question last summer when I was developing the time series class and the visualization class. What do I bring to the class? Right? Is it just that I am better at them than consolidating material from different textbooks? So what is the use? I struggled a lot with this to try to figure this out. So I have some thoughts on this, I'll tell you later. Other miscellaneous things that I observed, they really seem burdened with too many things to do. They have to run after my class, they have to run to U-Town for another class, and then they have to come back, and then they have to go to their residential college and do some activities, and then they have to do volunteering. Every student who asked me to write a recommendation letter sends me their CV, and there's volunteering. They spend some time volunteering somewhere. That's amazing, right? Without it, they lose out, because someone else who has the same results, they do volunteering, they're more empathetic, so they get the job, right? So they have to compete. In high school, they're doing research programs. It's crazy. Then there's a huge demand from above and below. My opinion, okay? My opinion. There's a huge demand from above and below for instantly applicable knowledge. Right? Once they leave the class, they should be able to run the model and get an answer. Why? I mean, should we really give in to this? What is our role again? What are we preparing students for? Right? If we just churning out cookie cutter who can run the models, students are very good at finding code, cutting and pasting and using it. They are really good. Okay, I'll tell you about my honors year project later. But they're really good at taking other people's code and running it. But if you ask them to write it from scratch, they may not be so good. If you ask them, what's this function for? Why did they define this class? What is this algorithm doing? They won't be able to answer you, right? So is this what we want? Is it our job what is our job, right? So where do we go from here? Okay. So let's summarize what has been happening, right? So the democratization of statistics has moved statistics away from the esoteric towards the immediately useful. Everybody needs it. Right? Everybody needs it, everybody needs to know how to interpret it, everybody needs to know how to use it, how to act on statistics that you show them. The amount of data has exploded due to data gathering techniques. And I'll tell you a bit about how I capitalize on this. We need to move away from an information transfer model to a constructivist view of learning. Get the students to construct the knowledge on their own. Okay? How much probability do our students really need? Right? When I go out, I tell them, after 13 weeks of material, what you must remember is the law of total probability. So what have I been doing for the other 13 weeks, right? Is it really necessary? They can always look up in a book, right? For the PDF, the PMF. Data analysis should be central to our courses. So I'm talking about data science and statistics courses, not the archaic models, not how to define, how to be so clever as to include this effect as a random effect and that one as a fix so that you get out the answer you want. All that sounds reasonable, right? But 100 years ago, H.G. Wells already said that it's necessary to be able to compute, to think in averages and maxima and minima, as it is now to be able to read and write. Okay, so all of you are nodding, and so you agree with the things that I said, or you just think, wait for this guy to finish. So, right. So I kind of tricked you, okay? All the points in this section were made by a statistician, David Moore, 22 years ago from Purdue. It's the same things we're hearing right now, barking up the same tree. So what's the conclusion? I can only make a couple of conclusions. One, so we can conclude that universities don't change. They're so set in their minds that even after 22 years, we are not changing. Right? So we are so stubborn, we still think we're better than the industry, we know what the students are supposed to know, and we insist on just teaching them that way. We don't want to change. But the other day, I heard someone high up in the university telling me that universities are adaptable. In 22 years, we haven't adapted. Is that true? Or the other conclusion is we're changing, but we're not changing fast enough. Or we're changing, but the environment outside is changing, so we need to be changing constantly as well. So whatever the case, I think there are some lessons to learn, and we need to see what we can do. Okay, so this is just a quote about, because I'm trying to bring out what is it that a statistician does, and what should we be teaching them, and how, right? So I know the difference between a statistician and a computer scientist. A statistician fits 10 parameters to the data and tries to get it right. A computer scientist fits 10 million parameters and tries to get an answer. Okay, so this is quoted by someone. And now this is not saying that the computer scientist is right. Okay, so the answer might not be the right one. Okay. But my point is this. We need to think about what a statistician is and then work towards that. So we need to, I will come to this at the end, we need to list down the skills that a statistician, or the knowledge that a statistician should have, and then work towards it. And once we do that, the framework becomes simpler. We can assess how well we're doing, we can track what we're doing, we can update that as we go along. So I'm not creating extra work for Tiong Wei and all that, but I'm not saying we should do that right now, but we should think about it, right? So here's my experience. I think they still need a solid theoretical background in probability and mathematical statistics. Without that, they cannot tell right from wrong. So yes, they can go outside and read a lot of material, they can decide how to apply the models, but do they know if it's correct? So what do I want to instill in my students? So suppose, the other day I heard this case study. Suppose that we want to assess whether there's a difference between certain colored taxis, let's say yellow taxis and blue taxis. We see a time series of the yellow taxis, the number of accidents that are involved with them, and then the blue taxis, the number of accidents. And then someone suggests go and do a t-test. What I want my student to be able to say is, hey, should we really do a t-test? Because those are clearly correlated observations in time. T-test requires independence. But if you just pick up the knowledge from online, you will just go and apply it. Hey, two groups, I just apply a t-test. So that's what I think we should be instilling in our students. And without some rigor in mathematics and probability, they won't have this. They won't, I feel, again my opinion, I feel they won't be able to extend the knowledge that we give them if we don't give them how to test whether something is right, how to develop something on their own. Okay? But yes, from my experience in the industry, they need to be very good coders. When I was at IBM in 3 years, the most valuable thing I learned there was Git, which is a version control for code, source code. Right? So now it makes my work much more efficient. They need to be able to do this, to pull data from various sources, clean it, manipulate it on their own. So let's try to prepare them for this. Okay, they need this skill, so let's do it. So here's how I do it. Oh yeah, yesterday I attended a talk by Alsat, and then she ended with a poem by Rudyard Kipling. So I felt I should give you a poem from another great poet of our times. All right. So we have to, what I'm saying is we have to decide what a statistician should be, and then we work towards it, or a data scientist, or whatever you call them. So here's how I tried to do it. In my time series and visualization classes this year, every single tutorial was a data analysis exercise. So I ran all the tutorials on my own. This is a group of about 150 students each time. So I have to set the data analysis. I have to make sure that what we do in class is tied to what they do in the, what we do in the lectures is tied to what they do in the class. In addition, I assign them DataCamp courses. So they practice that. DataCamp gives you a very superficial knowledge of the coding. But then they apply it in the class and it sticks in their mind. So here's some feedback. Again, this is selective, right? So you should keep in mind, whenever people give you feedback, out of every 5 people who give you feedback, one of them will love everything you do, one of them will hate everything you do. It's the other 3 that you need to pay attention to. I've picked those who love me, right? Some of them went on to sign up for DataCamp on their own. Okay? One of them told me that through the exercises, he learned things that he wouldn't have learned online because he had to put together the skills, right? in the topics, we give them separate skills, but during the tutorial, when I throw him a data analysis, I put missing data, I put one of the fields as with a hexadecimal code, so they has to figure it out. He has to try to put the information together and solve it on his own. And that is something that they cannot get by learning online. So we have to put them, I feel, we have to put them through the process so that they experience this. I did get negative feedback. So here's one of the feedback. So during the visualization class, I made them plot a graph using graph paper by hand. Now I do this a lot. In my office, if you come, you'll see a lot of plots of graph paper. Because of that, I internalize data about myself. I know that for grading, it takes me 1.5 minutes per script. Every day, I spend about $4 on lunch from 8 a.m. to 5 p.m. in school. On weekends, I drink more non-water. So I track a lot of data. I know that last year's probability exam, my midterm and makeup midterm, my midterm median was 12, my makeup midterm was 19. So I really screwed my students there. Right? So I plot a lot of data on my own, and I tried to get them to do it. So some of them appreciated it. The idea is that without a code, without programming, can you make the plot that presents the information accurately? But some of them don't like it. They say, do we really need to make a plot using graph paper? So I get negative feedback. I'll tell you about my probability exam. So in my probability exam, I can't run away from theory in that, right? So I try to stress to them that probability is a tool for decision making, right? So in my final exam, I try to construct a problem that is in this slide. So here's the problem that I gave them, right? Suppose that this is based on a true story. So in Florida, the police confiscated 500 white packets from someone who they thought there was a drug dealer. But they cannot test all 500. David has seen this question, so he knows this. Okay, so they tested 8 of them and found that 8 of them were cocaine. But they didn't test the remaining 492. So then I asked them to, so what they did was, they took a sample of 2 from the remaining 492, and then they sold it to someone on the street to entrap him. Because if you buy cocaine, you can be charged in Florida. So they sold it to this guy, and then they wanted to arrest him. So they ran after him and arrested him, but he flushed it down the toilet before they could arrest him. So they don't know whether those 2 packets were really cocaine or white powder. So then the lawyer argued, so I'm the lawyer, so police standing there, the lawyer is standing here. So the lawyer argues, hey, those 2 that you gave him were not really cocaine, they were white powder. The maximum probability that was white powder is this, and that's enough for reasonable doubt. So that's a hypergeometric distribution. They approximate it with a binomial, and they maximize the probability. So then the police argue back. So they have to compute their probability. Then the police argue back. Okay, so you tell me I have 490 packets here, right? So you tell me how many of those packets I must test in a row such that if all of them are cocaine, the probability drops to below reasonable doubt. So they go and compute that. So probability is used in a real life case to make a decision. Now it's not easy for me. Throughout the course, the students tell me, hey, this course is just about English. If I understand your English better, I'll be able to solve all the problems. During the hall, there's about 350 students, and I'm running around explaining to them, because that should not be what worries them, right? Whether they understand the English or not, that's reality. Later on, when they work, someone's going to give them a problem in English, they have to solve it, put it in the mathematical framework and solve it. They can't use that as an excuse. So in the exam, I run around explaining to them, I don't understand this, I don't understand that, but they do it. I don't know if they liked it or not, but I did it. So for my final year project, my students, so they were in a group and they got together, and then they decided to use, to see if they could tell if someone was lying using data from several sources. One, do you know what an Arduino is? An Arduino is a small device that you can use to capture data. You can attach many sensors to it. So we attach a heart rate monitor, we take a video capture of their faces, of people, we record their voice. So they collated about 30 of their classmates, and then they came up with an experiment. So they would put down 10 Pokemon cards, and then they would say, randomize. They say, okay, you pick this one up, and you lie about what's on the card. So they record their facial features, their audio, and their heart rate while they're lying, and while they're not telling a lie. And then they use a logistic regression model to try to model which features are significant. Now, they came up with this, so they own the project. OpenCV is open computer vision. There are a lot of algorithms in it for detecting face. They came up with functions on their own to track the pupil movement, the iris movement. So they developed these tools, they assessed how accurate these tools were, and then they ran the experiment on their classmates, and they fit the model. Now, they didn't find anything significant. I think it's because there was too much error in their measurement, which we already acknowledged. This is a measurement error model. But the whole process, they were very happy at the end. At the beginning, one girl said she felt lost, but then she realized how much she had done. She was very happy. Another guy, he was very impressed when he told them he used OpenCV to detect, to develop his own data collection tools and so on. So this was all from an informal exit interview that I did at the end. So some things I'm working, I think. I would like to do more of these. But what more can we do, right? Okay, so I think if we want to really go further in this, what we may want to do is try to identify the skills that we want a data scientist to have, and then track if we are developing those in them. So here are some ideas, right? So I wouldn't call myself a statistician if I didn't say this. I think we need more data, right? So what kind of data? So here's what we decide. I was reading this book by Mostella. Okay, Mostella is a guy, Tukey's contemporary. They are people who I idolize. So he wrote a book on stochastic models for learning. So this is how animals learn. So one of the ways they test how fast an animal learns is a runway. I mean, why am I telling you? You all are biologists, so you know about the runway model, right? You put a hamster at one end of a tube, then you put food at the other end, and you see how fast he runs down. Or you use a T-maze. So I'm not advocating that precisely we do this to our students, but we can do the analogous thing for human learning, right? One of the things that a data scientist needs to know is how to clean data, merge data, prepare data. So how about when in their first year or in the beginning of the course, we give them a data set with certain deficiencies in it that they have to merge, clean, and then plot. And we time them. And then at the end, we see how fast they're getting. So this is a very simplified example that I haven't even thought through. But if we can, instead of just giving them one exam, 2 hours, let's see how fast they do different particular skill sets, if we can. Similarly, when I set exams, I try to set progressive. After part A, if you can do it, usually you go on to part B and so on. Otherwise, they branch out. So this is like a T-maze, right? They get to the first branch, did they go forward? And we can track even the smallest things. We don't need handwritten paper anymore. We can do electronic. With the Exemplify software, it logs everything, all their keystrokes. When they switch back to this question, so we know, we have some idea they're thinking about this question. They may do this, then go to the next question, then come back, but we can accumulate how much time they spend on each question. We can really track these. With a good database of difficulty of questions, we can see how they progress over time over the year, whether our teaching is improving. Right, so that's all I have today. Okay, that's it.
Are there any questions for Vic? Well, we can ask him a lot more questions because he will be part of the discussion panel, which will start now. So let's thank Vic again for the very nice talk. So may I invite all the panel members, Alex, Vic, Shafiq, and Lai Hua, to come in front. Okay. Okay, this is the last segment of today's workshop, which from past experience, this is where the audience get to talk a lot more. And so there are mics at the aisle here. Like I said, the proceedings of the workshop will be recorded, so please speak into the mic. And the last segment here is that we would like to have a panel discussion and involving the audience about the evolving science education for Generation Z or Generation Z. Now, who are the people in Generation Z? Now, I also use Wikipedia. I went to the internet to find out more, and essentially, Generation Z were broadly classified as students who were born between the mid-90s, the mid-2000s. So currently, our students on campus now is roughly around that age group. Now, that age group, like I said in the beginning, they are technologically savvy. They like the social media very much. They are multitasker. They can do multitask very easily. They have a global outlook, and yet they have a short attention span. So we have together with me Vic, Alex, Lai Hua from pharmacy, and Shafiq Adams from Yale NUS. So maybe I'll get Lai Hua and Shafiq to share their perspective first before we open up to the floor about what are the changes in teaching them and what are the differences that we have experienced. Lai Hua is very experienced, a colleague that I respect a lot, that has been around much longer than me. Longer, sorry. Sorry. Longer. Sorry, in my desire to show respect to Lai Hua, I said something that I shouldn't have said. I'm sorry. So maybe let Lai Hua.
All right. Good morning to everyone. First and foremost, thanks to Se Song for those very kind words. Indeed, it's true that I've been with NUS for many years, but I don't think I want to tell you how many years, okay? You see for yourself. Okay, now before I share with you my thoughts about teaching pedagogy, I would like to thank the speakers who have shared with us their experience. In particular, I want to thank Alex again, somebody whom I have not met for some time, although we are actually neighbors, right? We never bump into each other so often now. And